Principles of Operating Systems, Chapter 6. Memory segmentation, division of the primary memory into segments, also called sections. Similar to paging, pages are of a uniform size, dictated by sectors on the size of a sector on a hard disk. Segments are not of uniform size. Pages are controlled by the operating system. Segments are described by programmers. When you're using a segmentation, a reference to a memory location is done by identifying the segment and offset within that segment. Segments or sections are also used in object files of compiled programs, then linked together into a program image, the whole image loaded into memory. They correspond to natural divisions of a program, individual routines, individual data tables, so that the segments are visible to, described by the programmer, as opposed to paging. Different segments can also be created for different modules or for different classes of memory. Division of a program into code segment and data segment, for example. They can also be created to be shared between different programs. In a system that uses segmentation, computer memory addresses will involve a segment ID and an offset. The hardware memory management unit is responsible for translating segment offset into physical addresses and for checking to make sure that the segment offset exists and that the reference that is permitted. Each segment has a length and normally has a set of permissions, read, write, execute, associated, determining what can be done with the data in the segment. The process is only going to be allowed to make a reference in a segment if the type of reference is allowed by the permission settings, and if the offset is in the range specified by the length of the segment. Otherwise, you get an exception, like a segmentation fault. Segments can be used to implement virtual memory, like pages. In this case, then the MMU, Memory Management Unit, would have a segment table, pretty much similar to a page table. Each segment entry then would have an associated flag indicating whether that segment is present in RAM or not. If a segment is accessed and it's not present in RAM, we get an exception raised and the operating system reads the segment into memory from secondary storage. Segmentation, implemented in several different ways on different kinds of hardware systems, sometimes with, sometimes without paging. The Intel x86 kind of introduced the idea of memory segmentation, but it doesn't fit either of the above models. The memory segmentation did not provide any protection. Any program running on an x86 can access any segment. There are no restrictions. Segments are only identified by starting location. There was no length checking, and this obviously created serious security problems. Starting with the 80286, they did start providing protection. Virtual memory with segmentation works pretty much the same way as virtual memory with paging. The code and data are divided into segments. The segments can be stored on disk and loaded individually as needed. And they can be copied back to secondary storage when they might not be referenced very soon. So that segments in a virtual memory system with segments function pretty much the same way as pages in a paging virtual memory system. Since segments tend to correspond to logical subdivisions in a program rather than to physical subdivisions in data storage, there will be less swapping in and out in a segmented virtual memory system than there would be in a paging system. Often, most of the code is going to be compiled into the same segment, so all coding references will be to commands in the same segment. All of that will be loaded into RAM together. Related data will tend to be contained in the same data segment and would be loaded in together. So segmentation systems will be less subject to thrashing than will paging systems. Because segments are not uniform size, virtual memory systems using segmentation are subject to fragmentation. There are techniques to avoid or at least reduce fragmentation in the segmented virtual memory systems, but they all add significantly to overhead. The principle of locality works in the other direction too. They have developed new technologies for RAM that works faster, gives faster memory readings and writings. Unfortunately, faster RAM is more expensive. It's not cost effective to build computers using all of its RAM with the high-speed technology. But it is possible to include a small section of RAM with high-speed technology. This high-speed section is called a cache. Now, when a CPU references a cell in a section of RAM, then the principle of locality says that probably the next few memory references are also going to be in that same section of RAM. That way, then, they can use small sections of high-speed RAM and copy the contents that are likely to be referenced soon into the high-speed section. That way, most of your memory references are going to be using high-speed RAM without having that much high-speed RAM in the computer. If a CPU references a cell in a section of cache, the high-speed section, then it's likely the next few memory references are going to be in the same section, also making use of high-speed references. If the processor references a section in normal, not so fast RAM, then they can copy that section of RAM into the cache, and by the principle of locality, next several memory references are going to be using the high-speed section, or can be done using the high-speed section. This way, although if you only have a small amount of high-speed memory, you can, in fact, have most of your CPU operations executing using that high-speed memory. You get most of the benefit without all of the expense. Of course, in systems with cache memory, it's the operating system that has to keep track of which RAM sections are duplicated in cache, which of the cache sections have been referenced recently, which cells in cache have been modified so that before overwriting that section, they have to be copied back into RAM. Just as with the virtual memory, cache memory is subject to thrashing. Effective replacement strategies are critical to the success of a cache system. Now, cache memory uses a system pretty similar to paging, but cache systems are smaller than pages. They're divided into standardized sections called blocks. So when a process references an address in RAM, the first thing that the system will do is check to see whether that location, that thing in RAM, is already represented in cache. If it's not, then the system tries to find an empty block in cache to move that RAM block into cache. If there are no unused cache blocks, then the system will choose one of the cache blocks and overwrite it. The contents of a section of RAM, the size of a block, and containing the referenced address gets copied into the selected block in cache, and the process continues using the contents of words stored in cache, not those in RAM, so that the system operates faster. As with virtual memory, if a block is going to be overwritten, then there are several algorithms to choose which block to swap back out and overwrite. One of the factors that has to be taken into consideration when the memory unit chooses a block to swap out from cache to RAM, is whether the contents of that block have been modified. If the cache data has been modified, then before the block is overwritten, it has to be copied back to RAM. Otherwise, the changed modification information is lost. And of course, since this is done using the relatively slow RAM, that's slower than just copying from RAM back into cache. Further, if the data in the cache block has been modified, there might be another process that, making use of the same data in RAM, whose cache version has now been modified. This could work out three different ways. System might keep a record of which blocks are in cache and allow the second process to use the same copy, the same block in cache. Or the system might copy any modified data back to RAM as soon as it's modified in cache. That way, the information in cache and the corresponding block in RAM are always the same. The system might just let the second process go ahead and use the data in RAM. Now, in order to allow several processes to reference the same block in cache, that requires extra cache memory to keep track of the records. This is extra overhead. And each memory reference has to use these records. Now, there's an extra problem in multiprocessor systems, since individual processors have their own individual cache built in. A second process processed by a different processor would not have access to the cache for the first process. If you're copying back to RAM every change in cache as it occurs, then remember, RAM access is relatively slow, and so you're losing much of the effectiveness of cache. Especially problematic if you're actually doing computation, making changes in data. An alternative, of course, if the second process accesses the data in RAM, it would then have to copy that back to its own section of cache. And if there has been modifications of by the first process, then the data being used by the second process is dirty, wrong. It's going to be modified as soon as the first process data is copied back to RAM. Cache algorithms or replacement algorithms are algorithms that can be used to manage the cache stored on your computer. When the cache is full, the algorithm is used to choose which items to discard, swap out, make room for new ones. There are two measures used to determine the effectiveness of the management of the cache: latency and hit rate. There are other less important factors affecting cache performance as well. Hit rate, or hit ratio, is how often a searched for item is actually found in the cache. Latency is how long after a desired item is requested that the cache can return that item, how long it takes. Hit rate, more efficient replacement policies keep track of more usage information in order to improve the hit rate. Hit rate measurements typically are done on benchmark application, since they're going to be different from different programs. The hit ratio varies widely from one application to another. Video and audio streaming applications have hit rates close to zero. Each bit of data is read once and used and never retraced. Even worse, many cache algorithms, at least LRU in particular, allow this streaming data to fill the cache, pushing out cache information that will be used again. Latency, faster replacement strategies typically keep track of less usage information, or for direct cache, no information at all, to reduce the amount of time required to update that information. Each replacement strategy is a compromise between hit rate and latency. There are other factors, too, that have to be considered. Some items have different cost. It's better to keep the items that are expensive to get in the cache as opposed to those that can be replaced more easily. Some items will take up more of the cache than others. If they have different sizes, you might prefer to discard a larger item to have space to load more than one smaller one. There are items that expire with time. Some caches keep information that expires. News cache, DNS cache, web browser. The computer can preferably discard these items because they have probably already expired anyway. Replacement policies for cache are generally pretty much the same as replacement policies for virtual memory. First in, first out, least recently used, pseudo least recently used, time aware least recently used, most recently used, random, least frequently used with aging. First in, first out. With this algorithm, the cache is set up as a first in, first out queue. When the cache is full and a new block has to be read in, the cache eliminates, swaps out the oldest block. The oldest one, without any regard to whether it's popular, how many times it was accessed, when it was accessed. The oldest block is swapped out. Simple to implement, very low overhead. Least recently used swaps out the block that has been the longest without being referenced. Of course, that means you have to keep track of when each block was referenced. It's expensive to implement the algorithm in a way that always discards the one that's been the longest without being used. Normally, this is implemented using age bits for the blocks, the lines, and tracking the least recently used based on the age bits. In this kind of implementation, every time you reference a block, a line in cache, all of the other blocks' age bits get updated. For larger caches, LRU has significant implementation costs. For many CPU caches, a scheme that usually discards one of the less recently used items is good enough. And so many CPU designers build in a pseudo LRU algorithm. Pseudo LRU algorithms only need 1 bit per cache item. Typically, they will have a miss ratio a little worse than LRU, a little better latency than LRU, use a little less power, and have lower overhead than LRU. Time-aware LRU is a variation designed for situations where the contents of a cache have an identifiable valid lifetime. It's particularly suitable in some kinds of network cache applications, and especially for distributed networks. Most recently used. MRU discards the most recently used items first. Certain kinds of patterns of use in particular looping sequences, it's most important to keep the older blocks in cache. If a block is certainly going to be referenced again eventually, random replacement selects a candidate at random and discards it. You don't have to keep track of any kind of information about the access history of the blocks because you're going to choose, you're not going to take anything like that into consideration when a block is chosen to be swapped out. Because it's simple with low overhead, it's been used in processors, in particular the ARM processors. Least frequently used counts how often an item is needed. The items that have been used least frequently, least often, are discarded first. Similar to LRU, except instead of storing how recently the block was accessed, it tracks how many times it was accessed. LFU with dynamic aging is a modification of LFU. It adds aging to the mix to accommodate changes in popularity. So you get a cache age factor added to the reference count, counting how often they were. So that when a new object is added to the cache, or when one is re-referenced, we keep in track of how recently as well as how often the item was referenced. It increments cache ages when removing the blocks. If an object was originally very popular, accessed very frequently, but then becomes less used, newly more popular objects can move ahead of it.